Today, actually, we're going to be looking at Uber DeepETA. So you can think of this as like their deep learning approach towards predicting arrival times across all their services that they're providing. For instance, let's say you make an order on Uber Eats, so you will get an estimation of how long will that food get to you, or maybe it could be Uber rides. Also, you get an estimation of like the pickup. So I thought this was quite interesting how they went about this. Like they have detailed all their approaches, including they have written a paper about this. So there are certain techniques that I pretty much liked a lot, and I've learned a lot from actually going through the paper. So I will be actually explaining it in a much easier way for you guys. Without wasting any time, let's get into it. So, prior to the implementation of this paper, their previous system leveraged what they called a routing engine. The routing engine was made up of like shortest path algorithms such as diagram algorithm, which is mainly used to find the best path through a graph. So you can think of we're trying to find which is the best path to get from point A to point B. However, they did realize that actually these algorithms, they do not capture the condition on the road. For instance, let's say the driver decide to maybe take a different route. Let's say maybe there's a accident on the road, right? So we need to take these conditions because they impact how long it will take for the driver to get to the destination. Another point that they did raise was that they leveraged XGBoost due to its high accuracy and low latency in production. But the problem was that as like Uber is growing at this rate, the XGBoost was becoming unmaintainable due to the tree now becoming more deep. So the requirement of now the new system was that they needed to build a low latency system that could return estimate the time arrival in millisecond. We still needed to get the same accuracy, the one that we used. Like we still needed to get the same accuracy as XGBoost, so or maybe better or something like that. And the second one, the third requirement was generality. So the model that was supposed to be built is supposed to generalize across the Uber services. These include Uber Eats, Uber rides, and I think there's also like Uber shipping. So now looking at the high level architecture. So the core idea here was to combine the routing or map data with the traffic data. So the traffic data, you can think of it as the real-time data. So as events happen on the road, we incorporate them into our data. So for instance, let's say the driver decide to take a different route. So we're gonna have to take that into consideration. Maybe let's say the driver made a mistake. We're gonna have to take that into consideration. Uber has always had the map data. I think they also have a department about maps or something like that. But you can think of this data as like the division of the route network into small road segment. So then we represent these road segments by weighted edges in a graph. Then based on that, we use shortest path algorithm to find the best path from origin to destination. One could argue that, okay, why don't you then use the shortest path algorithms only, because they still estimate the time arrival. The problem with this was that they don't necessarily take into consideration the conditions on the road. For instance, the route uncertainty, we do not know which route a driver will take. So we need to factor those into our overall predictions. So we also have human errors, and I like this point whereby they state that we also could have to consider distribution shift. This is to say that it wouldn't be the same, like even if like you're coming from the same, even if it's the same distance for Uber Eats and Uber rides. So we need to cater into those type of services, because maybe for other services it might take time to reach the same destination or something like that. So given the limitation of using only the map data alone, like we said, we're going to take into consideration the real time and real scenarios on the road. So I want you to make some sort of like an example. So let's take, for example, Uber Eats. I don't know if you guys have ordered on Uber Eats, But you will see at some point, let's say you order on Uber Eats, and it estimates the time that it will take for the driver to get to your place. But then maybe along down the line, the time expand, the estimation expand. I think this is because of the conditions that are happening. For instance, on Uber Eats, maybe the restaurant this time is taking more time. Maybe the driver had to wait at the robot for more time this time around. So those kind of things, then they influence this time. So initially we were here, then the time now, the prediction increases. Maybe there was a traffic, I don't know, then the time increases, just like that. So I don't know if you guys have seen such a behavior, but I am assuming that this is because of the taking into consideration the conditions as they happen on their route. Due to the two components that we just discussed, which was combining the map and the real-time data, Uber then went ahead and proposed a routing engine and machine learning post-processing module. So you can think of now the problem was formulated as we're going to take the routing engine, which is denoted by this notation, and for each ETA request, we're going to take the timestamp and we're going to take the recommended route segment and we take the features. This then makes our formula to be we take this, then we try to predict this y head. However, it is important that here we're only taking into consideration the routing engine portion. So the author recommended that we should be able to take also the decisions that have been made by the driver, because we don't know if like the driver will take the recommended route. Now we're going to discuss the second component, which is the machine learning post-processing in more detail. I want to remind you that we said that we're going to take the routing engine. Also, we said that we're going to take the traffic data. So this, you can think of it as equivalent as traffic data. It's just that now we're discussing the features that we should take into consideration. So I want to make sure that you understand that this portion that we're discussing now is different from the routing engine. So what are the features that we'll be then considering? So the considered features considered of temporal features, which you can think of like minutes of the day, day of the week, or something like that. Then we did also take into consideration the geospatial features, which included latitude and longitude, and the trip. This also looked at the trip type, route type that was taken. And the traffic features included of real-time and historical speed. Then the context include of the country, region, IDs. Then the label, this problem is formulated as a regression problem. So we're going to have, the label is going to be the actual arrive time. So now we're going to look at the level architecture of feature processing. So we're going to go into too much detail into how all of these features are handled. But for now, I just want to give you a high-level picture of how these features are combined to make predictions. So we essentially have embedding modules which take the output from the routing engine, right? Then these output, then they go into another component which discretize them if maybe they are continuous features. So according to the experimentations that they've done, they've realized that actually discretizing some of the continuous values produce accurate results. Then we do actually have some sort of like calibration features. So you can think of this, they indicate if like this is a pickup or a drop off, right? Then we have an interaction module to learn the interaction of the spatial and temporal embeddings. So yeah, you can think of this as we're doing a dot product, but I think they did not do a dot product. So we're gonna get into how they were able to actually combine all of these features before they push them into the fully connected layer. The embedding modules were not cheap. They accounted 99% of their parameters. However, they leveraged them because they had a constant lookup. So I think this is quite important in production. I think it made the system much faster. So how did they then handle some of the categorical features? For instance, with the temporal features, which is time, what they did was to convert it into like minutes of the week, which according to me, I think this makes sense because the assumption could have been that Sunday it's not busy compared to Monday, and people are probably knocking off probably at 5 p.m. Maybe there's going to be traffic, so the minutes around this time are quite busy. So maybe there might be delays. So what they did is like they took 60 minutes, multiplied 24 and 7 weeks, then you get like 10,000. So this gave them like 10,000 embedding size for these temporal features. Then when it comes to the continuous features, what they realized after they've done a lot of experiment, they realized that actually using some sort of like discretization techniques can actually help to reduce to actually can actually help to enable more accuracies. So what they did was that they used some of these techniques. So for instance, I think we have uniform, whereby each pin has the same width across the span. We have quantile, whereby each pin has the same number of values based on the quantile, and we have cluster technique also. But they went with the quantile because it gave them more accuracy. So they bucketized their speed into 256 quantile. So now looking at the geospatial features. So here we try to understand how where features such as latitude and longitude were transformed. They leveraged geo-hashing technique and also leveraged multiple feature hashing technique. So the idea behind geohashing is to divide each region into a region of user-defined sizes, whereby each region is assigned a code, right? This is also known as a geohash. The question might be, why are we doing this? So it enables us to replace the 2D information, latitude and longitude, with a single code. So instead of having like those multiple longitude and longitude, now we have one code to represent a specific region also, right? So how it works is that you can have multiple resolutions. For instance, this is level 1, level 2, level 3. So given those codes, what they did was that they created a vocab. So each code had an index. Then they linked that index to an embedding layer. However, they did mention that doing it this way, then it took more space. They increased cardinality. So what they did was to try to see if like they can use feature hashing technique, whereby they map each grid to a multiple range of pins. With like multiple experiments that they did, they realized that actually having multiple feature hashing was better. It eliminated collisions. They used hashing techniques such as MemHash, which is a non-cryptographic hashing algorithm. So I have to say that these hashing algorithms that have been used, they are deterministic. I think the other one I think I've been using is called fingerprint hashing. Compared to hashing functions such as MD5, these hashing functions that are being used, I've never used this one, but I personally think they're fast. Like the fingerprint algorithm is quite fast and deterministic. So I'll try to look at this hashing function that they used, but I'm pretty sure that it's better than the cryptographic algorithm in terms of speed. Now guys, closing it with the modeling part and how they went about modeling. So essentially they built a wide and a shallow network with 2 layers. So how they kind of like combined those features, they used a linear transformer. So this was just to capture the interaction between features such as geospatial, temporal, and so forth. So some of you might be like, one of the requirement was to make latency low. Why will they use transformer? So they used a linear transformer, which essentially removed that quadratic time to linear time to O of n. So this essentially uh, made it faster or match the latency that they've always perceived with SGBoost. Then they used a linear layer which was helping them to adjust the bias for the request type, whether it's Uber Rides or Uber Eats. So I think the original author of the linear transformer, so what they tried to do was to express their self-attention as a self-product of the kernel feature map. So there's quite a multiple linear transformers. I think there's performer. So I think I've created a video about them. So you can check the video about how they work and how they are designed. But anyway, they introduced a linear layer which actually was meant to adjust the bias from the request type. I personally would love to know how this worked in more detail, because I find it quite to be quite good in a way that like all the predictions are catered for different request type. So yeah, I thought it was cool thing that they did. So anyway, from a high level architecture is that you have discrete continuous features, then you have embedding, you stack them together, you pass them throughout the linear transformer, which we can think of like it's a token mixer, whereby you kind of like take all of these features and mix them up. However, there was no positional embedding involved here, because there was no, it's not like we kind of like attending to all of these features as weights or as sentence. So it's like features, right? So just take that into consideration. Then what they did after that, they pushed the results from the linear transform into a fully connected layer. And the loss that they use a Haber loss, which you can think as like it gives you the best world of like mean absolute error and mean squared error. So yeah, I think that's all, and that's it. That is it to take from the Uber project that they worked on. I quite find it to be cool. I'll leave the link to the paper, to the blog. Tell me what you guys think, and let me know if you want me to cover like some of these projects these companies have covered or something like that. Thanks anyway. See you in the next one.